So the person watching just noted that you couldn't hear what was being said, so I apologize. I adjusted the volume on my microphone, but I did not have I didn't push the talk button. So I apologize for that. So the red circle here, this is a way to relate angular and translational parameters. So if we look at this equation right here, this actually helps us understand the whole why one trip around a circle is 2 pi radians. So if we've got delta theta, so in general delta theta equals delta S over R. Well, if we take one trip around the circle, so divided by the radius. Well, one trip around the circle is the circumference divided by the radius, so that's 2 pi r divided by r. The r's cancel out and we get 2 pi. So this drawing up here, notice for the first one, we've got a small radius, a small delta S. For the second one, we've got a large radius and a large delta S. But for both cases, delta theta is the same. And that's going to be an important principle for looking at some of these rotational motion problems. That if you're on a merry-go-round, for example, and you're on a merry-go-round, so one person on the merry-go-round is sitting at point 1, another person on the merry-go-round is sitting at point 2. The person sitting at point 1 is going farther around, or the person, I'm sorry, sitting at point 1 is not going as far around because they're, let's say, 1 meter from the center. They're undergoing a relatively small delta S. This person is 2 meters from the center. They're undergoing a large delta S. But since the merry-go-round is not shifting in any way, it's not stretching out, it's not made of Play-Doh or anything like that, they're both undergoing the same angle. So if they're both taking one trip around, I'll just not say one trip around, let's just say they're going maybe, a sixth of the way around the circle. So both points, 1 and 2, going, let's see, so pi over 4 radians, even though delta S1 is less than delta S2. So that is angular displacement. Just to quickly, so I guess I could have headed this, I headed this rotational kinematics because that was my first page. But really, the big theme here is angular displacement. So recall our definition of what we used to call regular velocity. Now we really need to call this translational velocity. Equals displacement over delta t. Well, if that's the case for translational velocity, then it turns out that rotational velocity is going to equal displacement over delta t. So in general, any classification of velocity that you want is the ratio of the relevant displacement to the relevant I can't even spell. EVANT. Trying to be cute here by squeezing the letter in, and let's just say I'm not cute. So relevant displacement to the relevant duration, which is just the name of delta t. In this case back here, we looked at the relationship between, so right here was relationship between a angular parameter, delta theta, and a translational parameter, delta s. Since translational velocity and rotational velocity have a similar definition, it makes sense that there's probably a relationship between the translational velocity and angular velocity as well. And by the way, I didn't mention this, but that is the Greek letter omega. It looks like a W, but that's omega, and omega happens to be the last letter in the Greek alphabet. If you're someone that reads the Bible, you know, there's a Bible verse, I am the Alpha and the Omega, the beginning and the end, because alpha is the first letter in the Greek alphabet. In fact, the word alphabet comes from the first two letters, alpha and beta alphabet. The last letter in the Greek alphabet is omega, and this is the lowercase omega. Looks like a W. So right here we've got our translational velocity. And just trying to keep some colors uniformity here. So V equals delta S over delta T, but delta S keep pointing to this circle here. Delta S, if we solve for that, is just going to be R times delta theta. It's going to be R times delta theta over delta t. Delta theta over delta t is just omega, so R times omega. If we look at the units of this, I probably should have done the formula up above and then the units down below. So let's just look at the units. So velocity is meters per second, and oftentimes when we analyze dimensions or units, we put these square brackets around here. That's going to be units of meters. So radius can be measured in meters. But yeah, man, what's the units of this delta theta divided by delta t? So units, sorry, I didn't write the word units very well there. Delta theta is equal to radians, and of course, delta t is seconds. So the units of omega is radians per second. And typically when we write radians, when we label radians, we don't actually count that as a unit that we put down. So we could also call this just 1 over seconds, or we could also call this seconds to the -1 power. So if we do this and we say this is 1 over seconds, then we can see here that, actually let's just do the pointer, otherwise it gets kind of busy. We can see that meters per second equals meters times 1 over seconds. So let's say that you're a purist though, and I'm going to use a different color. Let's see what's a color that I haven't used before. I'm going to use kind of a purplish color here. Let's say that you're a purist and you really like the radians per second. So what if we use units of omega as radians per second? How does that jibe with this right here? So we've got radians per second. And radius here is really the length unit per radian. So this is omega. This is r. So radius is really the relationship between the length unit and an angle unit. And that makes sense because if we look at this formula here, oh look, I'm going to point to it once again. If we look at this unit right here, we've got delta S is a length unit or a translational unit purely. Delta theta is an angle unit. Let me use my little finger pointer there. So delta S is a translational unit, a length unit, meters. Delta theta is an angular unit, which sort of makes logical sense that we can't go from a translational unit to an angular unit without some sort of a conversion. So I can't go from dollars to lira, Italian currency, without some sort of translation. So I need some number that says this number of dollars is this number of lira. I probably should have picked a currency that I know more about. Actually, I don't know much about any currency. But we need something to convert. We need something that says X dollars equals 1 lira. So we need a unit we need something that has both the dollar unit and the lira unit in it. Well, delta S only has a meter. Delta theta only has a radian. So R then would need to have a meter and a radian in it. So I might be making too much of this, but I thought this was really cool when I first thought of it. Because that always bothered me. Well, radian, that's just a fake unit. I think when I was in college, the professor just said, we just dropped the unit of radian. But we don't have to drop the unit of radian because the unit of radian is right here in the definition of radius. And even the word radius, it's obviously the same root as radian. So the radians cancel out. And we end up with meters per second. So I know a couple folks are listening right now, including the person that reminded me that I had forgot to turn my microphone on. Again, I apologize. So do either of you folks have questions? You can voice them, or you can just put them into the chat box. Let's work through a fairly basic example. So we've got a truck with this size tire, 0.42 meter radius tires, and it's traveling at 32 meters per second. So 32 meters per second. It's always good to have a sense of what those numbers are. And my general recollection is that miles per hour is about twice meters per second. It's actually more than that. I think it's about 2.2 or 2.25. So 32 meters per second is about 70 miles per hour. So that's a reasonable speed for a truck to be going. What is the angular velocity of the rotating tires in radians per second? So again, this is a fairly straightforward problem. And we've got our conversion here between velocity and, for translational velocity and angular velocity. And oftentimes, excuse me, oftentimes when I say velocity or when somebody says velocity, they actually mean the translational velocity. Almost always angular velocity is stated as angular velocity, and I should really get into the habit of always saying translational velocity, especially when there are two to deal with. But if I forget and just say velocity, I almost always mean translational velocity. And I think if I don't, the context should be pretty clear. But if it is not clear, obviously ask about that. All right, so V equals R times omega. Well, here, R is equal to 0.420 meters. V is equal to 32.0 meters per second, and we don't know what omega is. So omega equals V over R. So that's 32 meters per second divided by 0.420 meters. And I'm going to actually slip in there. Actually, I was going to use a different color, but no, I'm not going to for now. Radius, remember, is a length unit per radian. So we have, but I will use the light blue, that's kind of our cross-off color. The meters cancel out, and we end up with, look at my notes here, .2 radians per second. So if I had not included this in here, and oftentimes books don't, I would have had to just insert that radian, and it would look like I'm making a unit up. That's why I like to think of the radius again as meters per radian. So this is 76 radians per second. We want to know what this is in revolutions per minute as well. So 76.2 radians per second. So if you remember from our unit conversion that we did a long time ago, we know that 60 seconds is 1 minute. So now we can cancel out seconds. But this is just radians per minute, and that's not what we want. We want radians per second. So we have another ordered pair here. Is this actually an ordered pair? I think so. So we want to get rid of the radians. So this might not be quite as intuitive. We want to get rid of radians and go to revolutions. So a revolution is a trip around the circle, right? Didn't the Beatles sing about that? You say you want to trip around the circle. So one revolution is one trip around the circle. And of course, one trip around the circle is 360 degrees, or 2 pi radians. So go to our cross-off color. Radians cancels out, and we end up, I guess it's our cross-off color and our circle the correct units color, or desired units. You can't say that there's a correct unit. That's going to be so 76 times 60 divided by 2 pi. That's going to be 728 revolutions per minute, and that's often abbreviated as RPM, where RPM means revolutions per minute. So this unit and this unit say the same thing. It just gives us some practice manipulating the equations. So questions or comments on that? Okay, so we started with displacement. We went to velocity. In this case, displacement is angular displacement, so number of radians around a circle. Excuse me. Velocity is angular velocity, so that's radians per second, or we could also say degrees per second or degrees per minute. Typically, we use radians per second or revolutions per minute. But now acceleration. So acceleration, if you remember translational acceleration, it's not like physics changed, it is. Ratio of translational velocity to duration. And obviously that is A equals delta V over delta t. So here's a classical question. Here we have V1. Here we have V2. And if you look at those arrow lengths, which I've now obscured, tried to be careful. Let me move my circle up a little bit. If you notice here, V1 equals V2, or better yet, the magnitude of V1, of the vector V1, equals the magnitude of the vector V2. So if this is the case, so V1 equals V2, isn't the acceleration equal to 0? So folks that are watching, V1 arrow is a certain length, so that's, let's just say it's 10 meters per second. V2 is 10 meters per second. So is there acceleration? The question then, is there acceleration in this case? All right, and one person said no. V1 is 10 meters per second, so if V1 is 10 meters per second, V2 is 10 meters per second, it seems like acceleration would be 0. But to go around a circle like this, there needs to be, so we can look at this in two different ways. It turns out that there is acceleration. I'm going to underline that. There is acceleration. And we can explain this in two different ways. Way number one is, in order to go around in a circle, so to turn a corner, to go around in a circle, there needs to be some sort of force. In the time of the ancient Greeks, Aristotle, I believe, was one of the people that thought a circle was perfect motion. So things up in the heavens went around in circular orbits around the Earth. That's because they were up in the heavens, and the perfect motion of the heavens is circular. But now we know that no, the quote-unquote natural motion of something is in a straight line at a constant velocity, which is a bit redundant. So it doesn't speed up, slow down, or change direction. That's what would be, in the absence of any forces, that's what would happen. In order for something to go around in a circle, there needs to be a force to pull it or push it in that circle. So the Earth, for example, goes around the Sun. That's going to come up later in this chapter, and that's the reason that this chapter ties together gravity and orbital motion with circular motion. There needs to be an applied force. So the Earth goes in not quite a perfect circle, but pretty close. It's actually an ellipse, but it's very close to being a circle. It does that because of the pull of the sun. If the sun were to all of a sudden just disappear, if some alien species were to pluck our sun out of the solar system, make it disappear, the Earth would just travel off in a straight line. It would no longer go in that circular motion. So one explanation, there needs to be an applied force. If there's force, there's acceleration. So just like whenever there's fire, there's going to be a flame. Whenever there's a net applied force, there's going to be acceleration. So that's one way to look at it. Another way to look at it is, even though the magnitude of the velocity is the same, the direction of the velocity is different. So the vector v1 is in a different direction than the vector v2. So if the directions are different, delta v is different. So that means that the vector v1 does not equal the vector v2. And that makes sense. So if I am pushing a box to the north with a force of 10 meters, and Amanda's pushing the box to the south with a force of 10 meters, those two forces don't equal each other, because they have, if each of us does it individually, there's a different result for the box. Me pushing the box north results in a change of motion to the north. Amanda pushing the box south results in a change of motion to the south. And those are not the same action, because if you're pushing from your living room to your bedroom, and Amanda's bedroom is south, then she's going to push the box south. She's not going to push the box north. That doesn't make sense. So because vectors have direction, two vectors that have the same magnitude but different directions are not the same vector. So since the vector v1 is not equal to the vector v2, that means that delta v also does not equal 0. And there's a picture of this right here. And they don't have the little arrows there, but the fact that the vectors, these letters are bold letters mean vectors. So questions about that concept, the fact that even though the magnitude is the same, you can't just say, oh, 10 meters per second minus 10 meters per second equals 0, so no acceleration. Questions or comments on that? So what is that acceleration? Well, the book, our OpenStax College Physics book, goes through this sort of fancy derivation. I'm not going to go through the fancy derivation. But it turns out that that acceleration that is going around in a circle, so this a sub c is the centripetal acceleration, as I've headed the page here. So the centripetal acceleration is v squared over r. Again, you can read the OpenStax College Physics book and see the derivation. I don't want to spend time on that. So let's just quickly look at one iteration of the formula. So a sub c equals v squared over r. But from a previous page, we see that v equals r times omega. So r times omega squared over r. So we get r squared omega squared over r. So one of the r terms on top cancels with the r term on the bottom, and we end up with r omega squared. A couple applications of that. A car, so here's a car going around the corner. It's a pretty busy road that this cow is nearby. So here we've got a cow near a busy road. So this car could be going around the corner at a uniform speed, a constant speed, or it could be actually speeding up. So its speedometer could continually say 30 miles per hour, or it could be changing from 30 miles per hour to 31 to 32 to 33 to 34 miles per hour, or from 30 miles per hour to 29 miles per hour to 28 miles per hour, and so on. Even if it's always reading 30 miles per hour, there's going to be acceleration. So there's acceleration because the car is changing direction. Another example of this is a centrifuge. So some folks watching this may do certain types of research in biology. Oftentimes a centrifuge is used, whether it's perhaps separating things out of a fluid or separating a solid out of a fluid, or perhaps separating two fluids from each other. A centrifuge is a way to thrust the more massive objects to the outer part of the circle here. So more move more outward. And they're not being pushed outward. They actually want to keep going in the circle, but the rest of the fluid isn't strong enough to keep them going in that circle, so they move outward. So let's do an example of that. Helicopter blades withstand tremendous stresses. In addition to supporting the weight of a helicopter, they're spun at rapid rates and experience large centripetal accelerations, usually at the tip. Calculate the magnitude of the centripetal acceleration at the tip of a 4-meter-long helicopter blade that rotates at 300 revolutions per minute. So we've got our helicopter blade, and let's just use blue for this. So we're told that omega equals 300 revolutions per minute, and we're told that it's the blade is 4 meters long, so that means from the center to the outer part is 4 meters, so R equals 4.00 meters, and we want to know the centripetal acceleration. So A sub c equals v squared over r, or r times omega squared. And in order to do this, in order to use this formula, omega must be in radians per second. And that makes sense because remember R is really meters per radian. So omega equals 300 revolutions per minute. One revolution is 2 pi radians. 1 minute is 60 seconds. Sorry, that's kind of a sloppy writing there. So it turns out we get 681 radians per second. And again, we have another sort of 2-to-1 ratio. If we double the revolutions per minute, more than double it, a little bit more than double it, we get radians per second. So that means that A sub c is equal to I was looking at the answers actually to a different problem, so this one is not 681. So 300 revolutions. Yeah, so, and that makes, that I should have looked at my numbers here. So here's a case where I spoke before thinking, because 2 pi is roughly 6. And here we have divided by 60, so we have sort of 6 divided by 60, which is 1 divided by 10. So to go from revolutions per minute to radians per second, you roughly divide by 10. So that is 31.4 radians per second. So now I'll actually keep my finger on the proper one here. So this is going to be R 4.00 meters times 31.4 radians per second squared. And that comes out to be 3.95 times 10 to the third radians per second. And then compare the linear speed at the tip to the speed of sound. So if we look back, we see that v is r omega. Four meters times 31.4 radians per second. And remember, this is meters per radian, and that's how we can get the radians to cancel out. (126 meters per second). And for the speed of sound, so the ratio to the speed of sound, 126 meters per second divided by 340 meters per second, that is 37%. So those helicopter blades are going at about 1/3 the speed of sound. So let me just close with this right here. A summary of rotational and translational parameters. Use a different color than black. So the rotational parameter is theta, and theta is related to angular velocity in this way. Translational formula is x, and that's related to translational velocity in this way. So we had a bunch of other formulas that we used before. Interestingly enough, all those formulas can be written in a parallel way with rotational motion as well. So if we wanted to solve more complicated rotational motion problems, we could use equations that are very much like what we've used before. So not only does x equal v0 x times time plus 1/2 axt squared, theta equals omega 0 times time plus 1/2 alpha, which we haven't got to yet. That's angular acceleration times time squared. Thank you for watching, and again, I apologize for the sound not working at the beginning. I forgot to turn on my microphone, so thanks again for telling me about that.